Hi, our next unit is on the states of matter. So we'll do a little comparison of the three states of matter, and then we'll focus the rest of our attention on gases for chapter 12. All right, let's start off with solids. The particles that make up a solid are touching each other. And what's really important is that the particles are not able to move past one another. So this has to do with the strong attractive forces between the particles of a solid. Those strong attractive forces keep the particles touching each other and also prevent them from moving around relative to one another. The particles making up a solid do not diffuse into one another because the particles are stuck in position. So the particles of solids do not mix with other solids or other substances, again, because those particles are held too tightly together to allow anything in between them. Again, because the particles of a solid are close together, they're touching each other, solids are usually the most dense state of matter. A notable exception is water, where the liquid form is actually more dense than the solid. This is why ice floats on liquid water. In table 12-1 on page 399, bottom of the page, we can see some examples of different substances and their densities as solid, liquid, and gas. And of course, we see there water is more dense as a liquid than as a solid. And we'll talk a little bit about the densities of gases. All right, liquids. Like the particles of a solid, the particles of a liquid are touching each other. The biggest difference between a liquid and a solid is that the particles of a liquid, unlike a solid, can move past or are able to move past one another. So though the attractive forces between the particles is strong enough to hold the particles together, it's not strong enough to prevent them from moving around. So the attractive forces between the particles in a liquid are a little bit weaker than the attractive forces between the particles in a solid. Because the particles are able to move past one another, the particles making up liquids are able to diffuse past one another. Liquids can mix with other liquids. Particles can fit in between the particles of a liquid. And as we saw in the table, a liquid form of a substance is usually slightly less dense than its solid form. So there's not a huge difference often in densities of solids and liquids for the same substance, but there is a huge difference in densities between uh, liquids and solids compared to gases. Solids and liquids that consists of a highly ordered arrangement of their particles are called crystals. We'll be talking about the types of crystalline solids later on in this unit. And solids and liquids are often referred to as the condensed phases because their densities are much higher than those of gases. Because the particles are touching each other, they are known as the condensed phases. So how about gases? Particles making up a gas are not touching each other. Why do you think that is? Well, we talked about what holds the particles of solids and liquids together, the strong attractive forces. So this implies here that the attractive forces between the particles of a gas are weak. So weak that the particles aren't even touching each other. And this then allows the particles to move past one another very easily. Particles making up gases diffuse into other gases very well due to the large separation between gas particles. So gases mix with other gases very easily. And as we saw on the table on page 399, gases are the least dense state of matter by far. In fact, we'll talk about it later on. Densities of solids and liquids are often expressed in grams per milliliter, whereas densities of gases, because they're so much lower, grams per milliliter is really not appropriate. As we can see in the table, we have some really small numbers, so better to express densities of gases in grams per liter, not milliliter. All right, so vocabulary term here. A gas that is created when a liquid evaporates or a solid sublimes is known as vapor. So for example, when water evaporates into a gas, the gas that is created is called water vapor. So gas, that term gas is mostly for a substance that in regular conditions, regular atmospheric pressure and temperature is a gas. Vapor refers to something that at regular atmospheric temperature and pressure is maybe a liquid or a solid, but it turns into a gas. That gas is known as a vapor. Some more vocabulary. Fluids are substances that flow freely. Both liquids and gases flow and thus are known as fluids. On page 400 in your textbook, you'll see a table there, table 12.2 in the margin. It shows the composition of the atmosphere. Our air that we breathe is mostly nitrogen. It's got a lot of oxygen and all kinds of other trace gases. So just a little heads up on the composition of the atmosphere. All right, so let's turn our attention to just gases. In fact, we have a whole unit on just gases coming up later on. So let's start with gas pressure. Pressure is defined as a force applied to an area. Force per unit area, though we're never going to use this equation. I'll write a mathematical equation. So you can increase the pressure by increasing the force, or you can increase pressure by decreasing the area that a force is applied to. In terms of gases and gases exerting pressure, gases exert pressure when the gas particles, and it says molecules here, and it could be atoms. It doesn't have to be molecules. When the particles of a gas collide with a surface, these collisions result in something called pressure. This outward force caused by the collisions between gas particles and the walls of its container is called pressure. Now, there's a couple different instruments used to measure the pressure of a gas. If you turn to page 401, on the left is a mercury barometer. A barometer measures air pressure. And so the air pushes down on the mercury that's in the container, and that mercury is pushed up inside that glass tube. And the distance that the mercury travels up that vacuum tube is the pressure in millimeters of mercury. Next to that, we have some manometers. There's actually two types of manometers. We have closed-end manometers and open-end manometers. So the ones shown in the textbook, those are open-end manometers. So on the flask side of the U-tube, if you will, the gas is exerting pressure. And on the other side, it's open to the atmosphere, and it shows in the textbook that the atmosphere, the air is pushing down. We have mercury inside that glass tube. And so the one in the middle, 12-1B, the mercury level is lower where the gas is. And so that means the gas is exerting more pressure than the air. And how much more pressure, as it shows there, whatever that difference in height is the difference in pressure. In 12.1c, the mercury level is lower on the air side, telling us that the air is exerting more pressure than the gas, or the gas is exerting less pressure than the air. How much less pressure is the gas exerting than the air? That would be determined by the difference in height or the difference in level of the mercury, shown in the book as H. Several units for measuring pressure. Here's 4 of them. Kilopascals is the first one, kPa. Is the SI unit of pressure. In fact, the derivation for kilopascals is shown on page 403 if you're interested in knowing where that unit comes from. Atmospheres is the most commonly used unit for pressure in chemistry. Millimeters of mercury, mmHg. And we have lastly torr, torricelli's, or just abbreviated as torr. So be familiar with each of these units of pressure, be able to convert from one unit of pressure to another. I'll show you how to do that in just a little bit. So what we're going to look at next is the relationship between the different properties of a gas. By different properties, I mean pressure, volume, temperature, and the amount of a gas. And so the mathematical relationship between different properties of gases are known as the gas laws. You don't need to know the names of each of the individual laws, but each of the laws has its own name based on the scientists who discovered the relationship between the said properties. Up with Boyle's law. Boyle's law shows the relationship between the pressure of a gas and its volume. Again, the name's not important. What is important is how they are related. The pressure of a gas is inversely proportional to the volume of the gas. Now, anytime we're looking at the relationship between just pressure and volume, we need to keep the amount of the gas, here it says number of moles, the amount of the gas constant, and the temperature of the gas constant, because both the amount of the gas and temperature will affect volume. And so we just want to see how pressure affects volume. So anytime two variables are inversely related, their product is equal to a constant. So if you took the pressure of a gas times its volume and multiply them, you'd get some number. If you change the pressure and change the volume of that gas and multiply those, you would still get the same number. And so then that leads us to this. If we can write it like this, P1 V1 equals K, P2 V2, so some other pressure and some other volume of that same gas is also equal to K. So we can just set those equal to each other. So P1 times V1 equals P2 times V2. P1 being the initial pressure of the gas, V1 the initial volume, P2 what the pressure of the gas is changed to, and V2 what the volume of the gas is changed to. Now you can use this formula or you can use the method that you learned in Chem Honors. I'm going to show you that with this example here on page 406. Read along with me, please. This is on page 406, 12.1. A sample of a gas occupies 12 liters under a pressure of 1.2 atmospheres. So those will be the initial conditions if we're using the equation shown in number 3. What would its volume be if the pressure were increased to 2.4 atmospheres? All right, so here's what you did in Chem Honors. You used ratios of pressures or ratios of volumes or ratios of temperatures or ratios of moles in order to do this type of problem. I just want to show you this way, and then you can compare to what's shown in the textbook. So I'm going to start off with the property of the gas that is not changing directly. So that would be the volume. So the pressure is changing, which we know then will cause the volume to change. So I'm going to start off with 12 liters. And I'm going to take this volume and multiply it by a ratio of pressures. Now let's think about this. We have to analyze the situation. How is the pressure changing? Well, the pressure is increasing. Now what we need to know is if the pressure increases, what effect will that have on the volume? Well, recall that pressure and volume are inversely related. So if you increase the pressure of a gas, its volume will decrease. And so that's important because that means whatever we get for this answer needs to be smaller than 12 liters. So this will help us to set up our ratio. So will the ratio of pressures be greater than 1 or less than 1? Well, if the pressure is going up, we know the volume is going to go down. We need to multiply this 12 liters by a ratio of pressures that is smaller than 1. So we're going to put 1.2 atmospheres on the top, 2.4 atmospheres on the bottom. Notice that not only is the pressure increasing, but the pressure is being doubled. If the pressure is doubled, the volume will decrease by the same factor, meaning the volume will be halved. So the new volume of the gas at the higher pressure, we want 2 sig figs, will be 6.0 liters. Again, look at how it's set up in the book and see the difference in these two setups. Example 12.2, same type of problem. A sample of oxygen occupies 10 liters under a pressure of 790 torr, which is about 105 kilopascals. At what pressure would it occupy 13.4 liters? So this time we're going to start off with the pressure, 790 torr, and we're going to multiply that by a volume ratio of volumes. Now, what is happening to the volume? Well, the volume is going up. In order for the volume to increase, what must happen to the pressure? Well, the pressure must decrease. So we're going to take that 790 torr and multiply it by a ratio of volumes that is smaller than 1. So we're going to have 10.0 liters on top and 13.4 liters on the bottom, and that will give us our new pressure. All right, why don't you try something like that on your own? Go to page 438 and try exercise 15. Do it whichever way makes most sense to you. Go ahead and pause the video and work on number 15 now. Setup, we have 2.5 liters of a gas. The pressure of that gas is increased, which is going to cause the volume to decrease. So we want to multiply by a ratio of pressures that is less than 1. So 1.00 atmospheres over 2.50 atmospheres. And that'll give us our new volume at the higher pressure, 1.00 liters. All right, take a look at 17. We'll just do letter A. Go ahead and solve that one. Pause the video now, please. Sample of krypton gas has a volume of 75 milliliters at 0.500 atmospheres. What would happen to the volume if the pressure was increased to 5.00 atmospheres? So the pressure is increasing by a factor of 10, which means that the volume will decrease by that same factor. So it's going to go from 75.0 milliliters to 7.50 milliliters. Before we look at the relationships that involve temperature, let's talk a little bit about the temperature scales, two that we use primarily in chemistry. One of them is based on particle motion. That's the Kelvin temperature scale. So recall that's the lowest theoretical temperature is 0 Kelvin, and that's results in, or a temperature of 0 Kelvin means that there is no particle motion. The more commonly used temperature scale in chemistry is the Celsius temperature scale. This scale is based on the boiling points and freezing points of water. So 0 Celsius is the freezing point of water. 100 Celsius is the boiling point of water. Now be careful, number 3. A degree in each of the above scales has the same size. So the difference between one temperature in Kelvin and the next corresponding temperature in Kelvin, say the difference between 1 Kelvin and 2 Kelvin, is the same as the difference between two corresponding Celsius temperatures. So they're the same size, it's just that these scales are shifted. And how much are they shifted? From Celsius to Kelvin, take your temperature in Celsius, and you're going to add 273, and that will give you the temperature in Kelvin. So the Celsius and Kelvin temperature scales are shifted by 273. Now technically it's 273.15, but I'm okay with 273. Make sure that you can go back from Kelvin to Celsius. So the reason why this relationship here is important is that we're often given temperatures in Celsius, but we need to use those temperatures, or we need to use the Kelvin temperatures in our calculations. Sometimes we get an answer in Kelvin and we need to convert it back to Celsius, so make sure you can do this both ways. So as mentioned, anytime, every time we're doing calculations involving gases, when you plug in a temperature, that temperature must be in Kelvin. That is why this is so important. Next up is Charles's law. Again, the name's not important. What is important is the relationship between the properties of the gases. Charles's law is the mathematical equation that shows the direct relationship between the volume of a gas and its absolute temperature. So the volume of a gas is directly proportional to the absolute temperature, or Kelvin temperature, of the gas. So again, just like before with Boyle's law, when we're looking at Charles's law, if we're looking at the relationship just between volume and temperature, we need to keep the amount of the gas constant and the pressure constant. This time we have two variables that are directly related, volume and temperature. So I'm going to rewrite this another way. So if two variables are directly related, their ratio is equal to a constant. Inversely related, their product is equal to a constant. So here, volume and temperature directly related. So we get V1 over T1 equals some constant K, some number. If you took that same gas and changed its temperature and changed its volume and divided that new volume by the new temperature, you would still get K. So if we set those equal to each other, we end up with Charles's law, which looks like this. V1 over T1 equals V2 over T2. Again, the ones being the initial conditions, the twos being the final conditions. Now again, be careful with temperature. Temperature must be in Kelvin. It is not going to be given to you in Kelvin, so you will need to convert it. So let's take a look on page 408 at example 12.3. Again, I'm going to set this up with ratios like I did with the other examples we did, and you can see how it's set up differently in the book. Read along with me, please. A sample of nitrogen occupies 117 milliliters at 100 degrees Celsius. At what temperature in Celsius would it occupy 234 milliliters if the pressure did not change? All right, so we're given two volumes, and so I'm going to use a ratio of volumes. So I'm going to start off with the temperature, not 100 degrees Celsius, but I'm going to take that and convert it to Kelvin. So if we add 273 to 100, we get 373 Kelvin. Going to multiply this by a ratio of volumes, and we'll just leave them in milliliters. Let's analyze this problem. The volume is going up from 117 to 234 milliliters. What must happen to the temperature in order for the volume to increase? Well, given that temperature and volume are directly proportional, the only way for the volume to increase is for the temperature to increase. So that means our answer is going to be bigger than 373 Kelvin. So that means our ratio of volumes needs to be bigger than 1. So I'm going to put 234 on top, 117 on the bottom. Go ahead and pause the video and get to that number, and then I'll show you how to arrive at the answer. So you get 746 Kelvin. The question, though, asks for the answer in Celsius. So how do we convert from Kelvin to Celsius? We're going to subtract 273. Notice it's not 273 Kelvin, it's the number 273, and that will give us the answer in Celsius, which happens to be 473 degrees Celsius. Go ahead and turn to page 439, practice problem number 25. Do A and B only. Go ahead and pause the video. Question asks, if the temperature increases from 18 degrees Celsius to 36 degrees Celsius, will the volume double? The answer is no, because technically the temperature is not doubling. It is doubling in Celsius, but the only way for the volume to double is if the Kelvin temperature were doubled. So we see that the Kelvin temperature is only increasing by a small amount, which means that the volume will increase by just a small amount. So we set it up here. We want a ratio greater than 1. Since the temperature is going up, it's going to cause the volume to go up, and we get a new volume of 32.9 liters. Compare gases at the same conditions. Scientists have set standards for both temperature and pressure. We abbreviate that as STP, standard temperature, and standard pressure. So the values of standard pressure, 0 degrees Celsius and 273 Kelvin. And then standard pressure in atmospheres, the different units of pressure, 101, technically it's 101.3 kilopascals, but I'm okay with 101. 1.00 atmospheres, 760 millimeters of mercury. Millimeters of mercury and torr are the same thing, so that will also be 760 torr. Now, I mentioned earlier that you need to know how to convert from one unit of pressure to another. To do so, use the values of standard pressure. They're all the same. So I believe these values are given to you on your reference sheet, so you don't need to memorize them, but do know how to use them. All right, we have one more gas law. It is known as the combined gas law. It is a combination of all of the gas laws. I left one out earlier. It's called Gay-Lussac's law. So the pressure of a gas and its temperature, like volume and temperature, are directly related. So this is called Gay-Lussac's law. It shows the direct relationship between pressure and temperature. So we can take Boyle's law, Charles's law, and Gay-Lussac's law, and combine them all into one gas law, an equation that shows the inverse relationship between volume and pressure, the direct relationship between pressure and temperature, and the direct relationship between volume and temperature. And this is what we get. So again, you can use this, or you can use the ratios of pressures and temperatures to find new volumes if you change the pressure and temperature. As noted, this combined gas law only works as long as the amount of the gas in moles remains constant. So let's take a look at an example. Go to page 410 and read along with me. Example 12.4, it says a sample of neon occupies 105 liters at 27 degrees Celsius under a pressure of 985 torr. This would be all of the initial conditions. What volume would it occupy at standard temperature and pressure? So keep in mind that standard temperature and pressure are not just words, they are numbers. So you can set this up using ratios. In fact, I'm going to do this in the space where it says exercise 33. Actually, no, I'm going to make a new slide and I'll show you how to set this up using ratios. This method is actually shown at the bottom of the solution. So you can either use a combined gas law. In using the combined gas law, you're solving for V2. So V2 is equal to P1 V1 T2 over P2 times T1. And you can see that in the middle of the solution. Or you can set it up with ratios. And so we'll start off with the volume, 105 liters. This time we're going to multiply by two ratios, a ratio of pressures and a ratio of temperatures. So the pressure starts at 985. It's going to be changed to standard pressure, which is in torr 760. So the pressure is going down. If the pressure goes down, that's going to cause the volume to go up. So our pressure ratio needs to be bigger than 1. Do the same thing with temperature. Temperature is going from 27 degrees Celsius to standard temperature, which is 0 Celsius. So temperature is going down, which is going to cause the volume to also go down. So we want a temperature ratio smaller than 1. Don't forget to change those temperatures to Kelvin. So 0 Celsius in Kelvin is 273, and 27 degrees Celsius in Kelvin is 300. And this will get you the correct answer. Turn to page 439 and work on practice problem number 33. You can use the combined gas law, or you can set it up with ratios, or do both and see which one you prefer. Go ahead and pause the video now. Here it is set up with ratios of volumes and temperature. Volume is going down, which means the pressure is going to go up. So we want to multiply by a volume ratio that is greater than 1. Temperature is going up, and that is going to cause the pressure to go up. So we want to multiply by a temperature ratio also greater than 1. I believe we want 3 significant figures in our answer. So we end up with 1,090 kilopascals. All the other units will cancel. We have Avogadros Law and Avogadros Principle, or Avogadros Hypothesis as it's written here. So two different things, they're related though. We'll start with Avogadros Hypothesis, which states that equal volumes of gases at the same temperature and same pressure. So we have two gases that have the same volume and the same temperature and the same pressure must contain equal number of molecules or equal moles as well. Equal molecules, equal number of particles, or equal moles of gases. Avogadros law, on the other hand, shows the mathematical relationship between the volume of a gas and the amount of a gas. It says the volume of a gas at a given temperature and pressure is directly proportional to moles of the gas. And so since volume and moles are directly related, we get something like this. Remember, that's the symbol we use for moles is N, so V1 over N1 equals V2 over N2. Now, we can take that and flip it around. If equal volumes contain equal moles, then equal moles of gases at the same temperature and pressure will occupy the same volume. The value for the standard, that's standard conditions, Standard molar volume of a gas is 22.4 liters, meaning 1 mole of a gas at STP, 273 Kelvin and 1 atmosphere, is 22.4 liters. Take a look on page 412. I want to show you something here with uh, molar volume. A bunch of different gases listed here. Take a look at the standard molar volume of each of these gases and see if you notice anything. They're not all exactly 22.4. In fact, they vary quite a bit. So this is only true. 1 mole of a gas will occupy 22.4 liters if we're talking about something called an ideal gas. 1 mole of an ideal gas occupies a volume of 22.4 liters. Here, we're talking about real gases. The volume of 1 mole of a real gas isn't always 22.4 liters. Real gases don't behave ideally. So later on in this unit, we'll talk about the factors that affect a gas's behavior in terms of it acting ideally or not. All right, take a look below that table on page 412, example 12.6. 1 mole of a gas occupies 27.0 liters and its density is 1.41 grams per liter at a particular temperature and pressure. What is its molecular weight? And what is the density of the gas at STP? All right, a couple different calculations here. So let me walk you through this. We're trying to find molecular weight, which is numerically equivalent to molar mass. So I'm going to set this up a little differently than the book shows. Recall, to determine the molar mass of a gas or any substance, we need to know the mass of that substance and the amount of the substance in moles. So we can use that information to find the molecular mass. Mass, we're going to use the density and the volume. So density 1.41 grams per liter. If we take that and multiply it by the volume, that's going to give us the mass. And the mass is 38.1 grams. Take that and divide it by the amount of the gas in moles, and it tells us in the problem that there's 1 mole of the gas. And so that gives us a molar mass of 38.1 grams per mole. So depending on the information you're given, ultimately we need to know the mass of the gas and the moles of the gas to determine molar mass. Now density at STP, we can find that. If you take a look at the bottom of the solution there, we can take the molar mass and multiply it by the standard molar volume of a gas, or the inverse of the molar volume of a gas. 1 mole over 22.4 liters. That's the volume that 1 mole occupies at STP. And then we can use molar mass and molar volume to find density. In this case, 1.70 grams per liter. All right, let's go ahead and turn to page 439 and work on practice problem or exercise number 39. Pause now. Should have mentioned just to do letter A, which asks for the concentration or molarity of this gas. I don't think it says molarity, it just says concentration in moles per liter. So we take the number of atoms, convert that to moles using Avogadros number, and we're given the value in atoms per cubic centimeter. So we got to convert the cubic centimeters to liters. 1 cubic centimeter is the same thing as 0.001 liters. And so we get our answer, which is 1.7 times 10 to the negative 16th moles per liter, or molar. Usually we express concentrations of gases in moles per liter. All right, so that concludes this lesson. Next time we will continue with the ideal gas law.